Hello everyone. Today, inshallah, we will go through the eigenvalues and eigenvector. This is a very important topic as we introduced in the previous session. Today I will go through it with you in details, so you will have all your work ready for you. I will start with a small definition about why we take eigenvalues and eigenvectors. Using eigenvalues and eigenvectors will help you out and to get similar matrices. And once you get a similar matrix to an original matrix that's involved in a system of equation or plenty of applications, actually a lot of STM applications, we can have advantages of the diagonal matrices if your matrix is similar to a diagonal matrix. So answering this question or tackling this issue might show things out. So reason for the use of eigenvalues and eigenvectors, for example, it makes your lives easier from taking advantage into their diagonizable matrices. For example, if you have a matrix like this one, which is 4, 3, -7, blah, 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 and to the power of 10, it means it's multiplied in itself 10 times. It's not going to be an easy task to do, but on the other hand, if this matrix was a diagonal matrix, multiplying it to 10 times, all you have to do is to multiply the principal diagonal elements to the power of 10, and then you will have the result that you are aiming for. So if I have two matrices A and B are similar, and if I succeeded in getting a matrix B which will try to change matrix B or to get a similar form, I will take advantage of all of this. So if A is similar to a diagonal matrix, then we can take advantage of its properties. So the search now is how to diagonalize a given matrix. It's very, very simple. Okay, I will go first through my way in getting such equations, and then I will go through details in your slides step by step. We will go back to the main slides shortly. So here, how to introduce the idea about eigenvalues and eigenvectors. Simply, if I have matrix A, and if I succeeded in finding a vector U such that lambda equal to lambda times I, okay? Lambda times nu. So if I succeed in getting such a thing, in getting a value of lambda, which if you multiply it in a vector and you multiply this vector in a matrix, they will be equal to each other. If I've tried to search for this formula, and if I try to adjust it a little bit, so it's going to be a nu minus lambda nu equals 0, taking nu, which is a vector as a common, you will have A minus lambda of I. Actually, from this equation, or from this matrix form, now we can extend our steps in order to get the values of the eigenvalues, which are the values of lambda. Those are the values of lambda. So the eigenvalues actually come from this, a solution of this matrix, or getting the determinant of this matrix, which is A minus lambda I equal to 0. Solving this characteristic equation will help us getting what's called the eigenvalues. Let's look at them once more on the slides, same ideas. So mainly, let A be a square matrix, a non-zero vector U. It's called an eigenvector of A if and only if there exists lambda eta or lambda or whatever, such that A times U equal lambda times U or eta times U. So if you manipulate this form and you've tried to get them all in one side, as I did, so it's going to be AU minus eta U. Taking U, which is the eigenvector, as a common, it will leave you with the equations that I'm telling you about, A minus eta I times U equal to 0. Solving this system of equation, or this characteristic equation in specific, will make you have your quadratic eigenvalues, which if you are working with an A which is 2 by 2 matrix, you will have a quadratic equation. If the matrix was a 3 by 3 matrix, you will end up having a cubic equation, and as we will see. The values of the eigenvalues is sometimes called spectrum. I believe to convey all the details about this issue, it's better just to check it with an example. So for example, this is matrix A, which is 9, 2, 2, and 6, and we need to find the value of eta, or the eigenvalues, the corresponding eigenvectors, and we will get the orthonormalized model matrix, which has a huge advantages. It's an orthogonal matrix, so the columns of this matrix are orthogonal to each other, and this will give you a great advantage that the transpose of this matrix is the inverse, so we will check that also. Also, it can be diagonalizable. If you have A transpose or A minus 1 times A times U, you will have a diagonal matrix with the principal diagonal or the eigenvalues. Okay, let's start the steps of getting first the eigenvalues. So I will start now trying to get number 1, the eigenvalues. So step 1, I will try to get the eigen, values corresponding to matrix A. The first step is to get the determinant of the system that I told you about, which is simply the determinant of A minus lambda I equal to 0. And this is what is called a characteristic equation. So I will try to solve this characteristic equation. Also, all I have to do is to take this A matrix and then subtracting the value of lambda from the principal diagonal. So it's going to be 9 minus eta, 2, 6 minus eta, and I will put the value of this determinant equal to 0. Once you put the value of this determinant equal to 0, now I will have the equation that I told you about. I will start with multiplying the elements of the principal diagonal, which is going to be 9 minus eta times 6 minus eta minus 4 equal to 0. And this is a quadratic equation. So if I want to solve it, it's going to be really a piece of cake. So it's negative lambda times negative lambda, which is going to be lambda squared, negative 6 lambda, negative 9 lambda. So you will have negative 15 of lambda. 9 times 6, which is going to be a positive of 54. Just subtracting negative 4 from this system from this quadratic equation and equal to 0. I will now try to solve lambda squared minus 15 of lambda plus 50 equals 0, which is the quadratic equation that I told you about. In order to solve this equation, it can be easily factorized. So I can factorize this equation to be on this form. Okay, once more, this is the equation that I'm telling you about. This is lambda lambda. I'm searching for two numbers. Their multiplication is 50. And if you add these two values together, it's going to be 15. So I believe 10 and 5 looks tempting. And this is all equal to 0. So it's a lambda minus 10, lambda minus 5 equal to 0. And this is going to lead to that lambda, that lambda 1 equal to positive 10 and lambda 2 equal to 5. These are the two values which stand for the eigen values we need to evaluate. In order or corresponding to each one of these eigenvalues, so first of all, this part is okay. I will now go to get the corresponding eigenvectors for each vector of these vectors. I will start for getting u1, which is the first vector, which corresponds to lambda 1 equal to 10. Now, all I have to do is to try to solve the homogeneous system Ax equals 0, where A is exactly this matrix, but with replacing the value of lambda. So all I have to do is to just trying to make this substitution. So I will have the following. Okay? So it's going to be 9 minus 10. So it's going to be 9 minus 10, 2 and equal to 0. For the second row, it will go exactly the same, which is going to be 2, 6 minus 10. 6 minus 10 is going to be negative 4 and 0. This is the shape of this matrix. If I want to make the substitution in front of you, so it's a 6 minus 10. So all I had to do is to, step number one, getting the eigenvalues. Now I'm going to step number 2, which getting the corresponding eigen, okay, as I told you, vectors. I will make this substitution and then I will simplify this step, which is going to lead to the following. I will end up having a matrix on this form. 9 minus 10, which is going to be negative 1. This is 2, and for the final row, which is 0, for the second row, it will start with 2. Also 6 minus 10, you will have a negative 4 and then equal to 0. The coming step is really critical. For this stage, you should have either 2 identical rows, or at least you will have one row and there is a percentage connecting this row with the other one. So all I have to do is to be sure about this. The second step, I want to try to get to as close as possible to the reduced echelon form. So I will multiply the first row by negative 1. So I will have exactly the following. Times negative 1, so it's going to be a positive. Negative 2, then a 0. Then I will multiply by negative 2 and add on the second row. So it's going to be negative 2 plus 2, which is 0. Negative 2 times negative 2, which is going to be positive 4. Plus negative 4 is going to be 0. Same way like for the other element, it's going to be multiplying by negative 2 times 0, 0, plus a 0, so you will end up having 0. So this is the reduced echelon form that I'm telling you about. And this reduced echelon form, actually, it's a function in the component of the first vector. So all I have to do is to try to expand it once more into a vector shape. So I'm going to say this is the first vector first component. This is the first vector second component. Then I will try to expand. So it's going to be u1 sub 1 minus 2 u1 sub 2 equal to 0, which leads to u11 equal to a 2 of u1 and 2. So the first vector, which is u1, the first eigenvector, consists of 2 components, the first component and the second component. For the first component, I will make this replacement, replacing u11 by the value of 2u12, so it's a 2u12, which is going to give you a sub-vector space, and the basis of this sub-vector space as indicated for you. All I have to do is to consider a value of u12, let's say 1 or something, and then you will have a form, a nice form for this vector. So if I consider u12, you can choose it any way you like it. I will choose u12 equal to positive 1. So actually this is the first eigenvector, which is simply 2 and 1. Same steps, exactly the same, will be repeated, but this time will be with the second value of lambda. So now I'm trying to get the second vector, which is u2, the second eigenvector. I'm trying to get the second eigenvector, which corresponds to lambda equal to positive 5. So this is lambda equal to 5. In a similar steps, exactly the same steps, I will do it once more. I will start, as I told you, with our matrix, which is gonna be an A matrix minus lambda I equal to zeros. This is actually, once more, this is the system that I'm trying to solve. A minus lambda I as a matrix times the u vector, which equal to 0. This is my eigenvector, and I'm solving now for lambda 2. So all I have to do simply is to take these numbers, which is 9 minus lambda 2, which is 5, then 2, and it's equal to 0. Same for the second row, which is going to be a 2. Then I will have 6 minus lambda, which is 6 minus 5 is going to be 1. And this is going to be also 0. So once more, let me write it. Then I will use the substitution. It's 6 minus 5. Okay, once more, I will try to see what's going to be. So this matrix, after making these subtractions from the principal diagonal, I will have 4, 2, 0, and for the second row, it's going to be 2, 1, and 0. These are exactly the matrix that I'm aiming for. And still, I have either identical rows or there is a relation connecting them. So all I have to do now is to divide the first row, for example, on 4. So I would have 1, then 1 over 2 equal to 0. Then I will multiply the first row by negative 2, and I will add it on the second row. So negative 2 plus 2, the result will be 0. Negative 2 times half, negative 1 plus 1 is going to be 0. Negative 2 times 0 plus 0, so it's going to be 0. So now I'm ended up with, this is the second vector, first component, second vector, second component. Try to expand it once more as an equation. I will have u21 plus a half of u22 equal to 0, which means that this first component of the second eigenvector equal negative 1 over 2, the second component of the second eigenvector. Now I know for sure that u2 consists of two eigenvalues, which are u21 and u2 sub 2. Okay, this is for the second eigenvector. All I have to do is to make this replacement. So I will end up having the following. Replacing u21 by this value, which is going to be negative 1 over 2 u2 second component, exactly right. Then I will choose by myself any value for the second component of the second eigenvalue. Let's say for 2 or something. So I will consider u22 equal 2. Why to choose 2 exactly? In order to avoid these fractions. So if I use 2, so the result will be negative 1, then 2. Now this is the second eigenvector. I will write it over here. u2, which equal to negative 1 and 2. Now I want you to remark that we have evaluated two eigenvalues, lambda 1 equal to 10, lambda 2 equal to 5. Corresponding to each one of these lambdas, we succeeded in evaluating the first eigenvector and the second eigenvector. A small remark about this point, since you are dealing with a symmetric matrix, if you look at this matrix, you will find a symmetric matrix. You have the principal diagonal and the two elements on the side for the secondary are similar to each other. In such a case, you will have orthogonal set of vectors. How to check that these eigenvectors are orthogonal? It's very, very simple. If you get u1 dot u2, the answer will be 0. So if I multiply 2 times negative 1, the result will be negative 2, plus 1 times 2, which is 2. So the inner product of these two vectors will equal to 0, which means that u1 and u2 are perpendicular on each other. Okay, already checked once more. 2 times negative 1 is going to be negative 2, plus 1 plus 2, which is 2. The sum of them will equal to 0, and this stands for that these two vectors are perpendicular to each other. Now, for the first requirement, it's already done. I have the eigenvalues, and also I have the corresponding eigenvectors. Now I can get to the also normalized model matrix. It's really very simple. All I have to do is to change these two vectors into normal forms. How to change these vectors into normal forms? All I have to do is to divide the components of each vector on its magnitude. So all I have to do simply is to get the first matrix, which is U1, stand for the numbers which are 2 and 1, and for the second one 2, which is simply -1 and 2. In order to put these vectors on a normal form, it's really very simple. All I have to do is to divide these components on the square of the sum of the square root of the sum of squares of these components. So I will get the first component to the power of 2, which is 4, plus the second component to the power of 2, which is 1. The sum of these two values, it's equal to a root of 5. It's not a must for the second vector, but here they are exactly the same. Now I will get the B matrix, or the matrix that I'm searching for, which is orthogonal matrix and also normalized, because its vectors, its columns are the eigenvectors in the normal form. So it's going to be 2 and 1. This is the U1 eigenvector 1. And this is U2, which is -1 and 2. Simply, I will divide each value of these elements on the magnitude. So it's going to be divided by a root over 5, also divided by a root 5. Similar way, divided by root 5, and also divided by a root over 5. This is the form that I'm telling you about. This is the orthogonal matrix. And it is orthogonal and normalized also. One of the very top advantage of this also normalized matrix is its inverse is the same as its transpose. So if I make a transpose for this matrix, getting U transpose, it's gonna be the following. It's gonna be 2, then 1 over root over 5, and then you will have -1 over root 5, and this is 2 over a root over 5. This matrix is orthogonal, so it's easy to check U times UT will equal to the unit matrix, and if I use U times the A matrix that was given here times U minus 1, or the U transpose as we spoke, we will get a diagonal matrix where its diagonals are, or its diagonal in the elements of the eigenvalue. So it's going to be 10 and then 5, and these are zeros. And this is how to get a diagonalizable matrix out of a symmetric matrix. All of these steps I will repeat it once more for you on these slides. As you can see, we started with the characteristic equation. Try to put the determinant equal to 0, you will have a quadratic equation. Solve the equation, you will get two values of lambda. Corresponding to each one of these values, you will get an eigenvector. Just do your magic. Make the matrix 9 minus lambda, 2, 2, 6 minus lambda, replace lambda by the eigenvalue. You start to do the row operations in order to get to as near as possible to the reduced echelon form. Once you get to reduced echelon form, you will have your condition, resum, you will have your vectors, put them together in a matrix which is the orthogonal matrix. If you are dealing with a symmetric matrix, as it's going to be the case with our slides, as you will see down the road. Okay, this matrix is also normalized, which make you gain that its inverse is exactly like its transpose. It's a very rare property, but it's really very important. Okay, so once more, this is our matrix, 9, 2, 2, and 6. All I have to do is to use the spectrum, or find the eigenvalues, which is from A minus eta I equal to 0. Then the second step, I will take eta out of the principal diagonal elements. So it's 9 minus eta, 2 and 2, 6 minus eta, equal to 0. Try to expand it, multiplying the elements of the principal diagonal minus the elements of the secondary diagonal. This is the matrix, this is the quadratic equation that I'm telling you about. Okay, once more I will try to expand it. It's already expanded. Okay, try to factorize it once more. So I have lambda 1 equal to 5 and lambda 2 equal to 10. Remark, here it's really very good because I want to show you something. Here I'm solving for eta 1 equal 5 and lambda 2 equal 10. And the solution in front of you, I've just changed the two things, making lambda 1 equal 10, lambda 2 equal 5. It will make no difference. The system will adjust itself by itself. And you will get also the same characteristics from the diagonalization. But the diagonal matrix in this case will have a 5, then a 10, as you will see. Okay, second step, getting the eigenvector. So now we will solve the homogeneous system of equations. A minus E times I, the eigenvalues, U equal to 0. This system can be put on this matrix form, which is very, very simple. 9 minus eta, 2 and 0, 2, 6 minus eta equal to 0. We'll try to solve this system, which is very, very simple. Eta 1 equal 5, getting the corresponding eigenvectors. So this is the matrix. 9 minus eta, 2 and 0, 2, 6 minus eta and 0. I will replace these values by 5. So I will have 9 minus 5, 2, 2, 6 minus 5 equals zeros. So the result will be 4, 2, 0, 2, 1, 0. Exactly as I told you, two identical rows, or at least there is a percentage between them. So all I have to do is to divide by 4 the first row. So it's going to be 1. This is half, and that's 0. Multiply by negative 2, then add on the second row. This is what I'm going to have. The last step is to get one of them as a function in the other one. So the first eigenvector will equal to negative half the second component of the first eigenvector. Make your substitution. I will replace this one by negative half u12. Then put u12 equal to 2 in order to get rid of the 0.5 that's already existing here. So that vector is negative 1 and 2. Also, once more, remark that for alpha equal 5, I have negative 1 and 2. Exactly the same. For lambda equal 5, I ended up having negative 1 and 2 exactly in similar manner. That's what I'm telling you about. For continuing, for getting the second eigenvector, remark it to 10, all I have to do is to subtract the value of lambda equal to 10 from the principal diagonal. Here we go, I will subtract it from the principal diagonal, and it's gonna be 9 minus 10, 2, 2, 6 minus 10. Okay, once more, this is gonna be negative 1, 2 and 0. This is gonna be 2, negative 4 and 0. Okay, I will divide the first row on negative 1, so it's gonna be 1, and the negative 2 equal to 0. Then multiplying and trying to get to the reduced echelon form, I will have the form that the first component equal twice the value of the second component of this eigenvector. Similar manner, I will put u12 equal to positive 1, and I will end up having 2 and 1. Once more, I've switched the values of the eigenvalues. The eigenvectors are switched. This is the second, this is the first, because I used the lambda equal to 10. This is the second vector, eigenvector, which I ended up having negative 1 and 2. Once you used it for the first, it's negative 1 and 2. Now I can get, as I told you, there will be no difference. I will get the also normalized matrix, but before going to it, since we are getting the eigenvalues for a matrix which is element with a symmetric matrix, try to check if they are orthogonal. They are already orthogonal. So 2 times negative 1, negative 2, plus 1 times 2, 2, and the sum of them is equal to 0. That's, they are orthogonal in each other, as I told you previously. Step number 2, trying to get the also normalized model matrix. It's really very simple. All I have to do is to divide the first vector on its magnitude, which is the square root of the sum of the squares of the components, similar to the second one. So you will end up having your matrix on this form. -1 over root 5, 2 over root 5 for the first eigenvector, and that's for the second. If you make a change in the rows, or trying to get the transpose, and multiply these two matrices in each other, you will end up having a unit matrix. Really, this is the first, this is the second matrix. Either you multiply them U by U transpose, or U transpose times U, the result will be the same. So multiplying the first row by the first column, it's gonna be 1 over 5 plus 4 over 5. Same way goes for the second row, it's gonna be the same. The only difference is this is gonna be 1 over 5 plus 4 over 5, 5 over 5, which is 1. This one is gonna be -2 over 5 plus 2 over 5, which is gonna come up to 0. So you will have 5 over 5 and 0. Same way goes for the second row. So it is already checked that it is a unit matrix, which means that it's transpose in the inverse. If I want to make a diagonalization for this matrix, all I have to do is to get the A transpose times A times U, or A U minus 1 times A times U, where U stands for the eigenvectors matrix. Once more, this is the matrix, this is the A matrix that we started with, and that's its transpose. Then, if you do so, we try to multiply these two matrices, then you multiply it in the third one, you will end up having a matrix, diagonal matrix, with the elements of the principal diagonals are exactly the eigenvalues. It's exactly what happened here, it's the same as here. But here, I've used lambda 1 equal to 10, lambda 2 equal to 5, and it adjusted itself, as you can see, between the two sides. For this part, you have one more problem, just tickling this part. So that's another problem, which has 1, -5, -5, and 1, and also it's a symmetric matrix. So it's really very simple to get its eigenvalues. Once more, I will regain the characteristic. This is the matrix that I'm telling you about. I will get the characteristic equation, which is simply subtracting the minus lambda from the principal diagonal elements and trying to expand your equation. It's gonna be a quadratic equation. Once you try to expand it, you will end up having a matrix like this. A quadratic equation like this, which can be simply factorized to 6 and -4. These are the values of lambda. Corresponding to 6 and corresponding to -4, I will go and get the corresponding eigenvectors from solving this system of equation. 1 minus eta, -5 and 0, -5, 1 minus eta equal to 0. Exactly 7 steps. Now I will make the substitution, replacing eta 1 by 6. If I did so, it's going to be -5, -5, as I told you. So I have two identical rows. All I have to do is to multiply -1 and add to the second row. You will have the first, which is 1, 1, 0, and the last one will be equal to all zeros. Which means U1 sub 1, or the first eigenvector, first component, will equal to the negative of the first eigenvector, second component. Okay, start replacing these values from your first vector. So U1, the first component, second component. I will replace the first component by the second with an opposite sign. So this is how it goes. I will make an assumption, putting U1 to equal to +1, for example. I will end up having the matrix which is -1 and +1. This is the eigenvector, corresponds to lambda equal to 6. Same way like, if I use the lambda equal to -4, making exactly the same substitutions, taking negative eta or taking eta from the principal diagonal elements, I will end up having a system like this, which is 5 minus 5 minus 5 and 5. Then I will try to simplify it as much as possible, and I'm trying to get to nearest to the reduced echelon form. So I will have to do is to multiply by positive 5, adding to the last row. It's all eliminated. The first component equal to the second component. This is the condition. So for the second eigenvector, I will replace the first component by the second, considering u by 2 is equal to 1. So this is the eigenvector that which corresponds to negative 4. Also, since your matrix that you started with is a symmetric matrix, you have these two vectors which are orthogonal on each other. So you still will have an advantage from the also normalized model matrix. So remark, negative 1 times 1 plus 1 times 1, the sum of them equal to 0, which means these two vectors are perpendicular on each other, as I told you. Now to the part of the normalized model matrix. All I have to do, this is the first vector, u1, this is the second, both of them divided on their magnitude. This is u and this is u transpose. If you multiply them together, you will get a unit matrix. If you sandwich them by the original matrix, you will get a diagonal matrix with the elements of, okay, just a second, with the elements of the lambdas on the principal diagonal. This is 6 and this is -4, exactly as we did in the previous example. Also, you have another problem, 16, 12, 12, and 9, also symmetric matrix, and so on. Exactly the same. You can go through them. This is the value of the quadratic equation. Solving it, it's 0 and 25. The eigenvalue corresponds to 0. It's going to be similar. And this is negative 3 and 4. The eigenvalue corresponding to 25 is going to be 4 and 3. If you check the relation between u1 and u2, these two eigenvectors, you will find them perpendicular on each other or orthogonal. Also, in a similar manner, I can get the value of the matrix that I told you about, okay, which is the also normalized matrix, multiplying it by its transfer, by its transpose, you will end up having a unit matrix. Sandwiching u transpose A and u or vice versa, you will have a matrix with a